Good morning to all of you, my students. Today I will start my lecture 3. I have given to all of you exercise to verify the classification of bands, the graph which I had given you on the WhatsApp. Today I will tell some more thing about this. See, this is band. Band, I already told you, that is the semigroup, which is idempotent semigroup. Idempotent semigroup means that every element of the semigroup is idempotent. That is A square is equal to A for every A belongs to S. Correct? And I have also given you the example of the band semigroup. Now, Petrich, semigroup theorist, well-known semigroup theorist, Petrich had given the classification of bands. What he did, he just imposed conditions on bands. For example, if A square is equal to A is already, because it is a band. Now, if you impose one more condition, then what will happen? The structure will be decreased automatically. This is big structure, band. Now, when you impose one condition more, for example, if you impose a condition that is AX is equal to AXA, what happens? Size becomes smaller when you impose conditions. So in this way, this is for example the top left semi-regular band. Left semi-regular band means it is a band that is A square is equal to A and AXY is equal to AXY, AY, XY. So those two conditions make left semi-regular band. But size of left semi-regular band decreases. It is smaller and it is contained in bands, isn't it? Or also you can say it is a sub-band. So this is left semi-regular band, this is left semi-normal band, this is left quasi-normal band, this is left regular band, this is left normal band, this is left zero semigroup. And these are the right ones. That is dual of left. Right semi-normal band, right semi-regular band, right semi-normal band, right quasi-normal band, right regular band, right normal band, right zero semigroup. And in the between, semi-lattice, rectangular band, normal band, regular band. So what are the relation in between this? See, in the bottom, when we go from bottom to top, the size of the band, size of the type of band increases. Means left zero semigroup is smaller than left normal band. It is contained in left normal band. And left normal band is contained in left regular band. Left regular band is contained in left quasi-normal band. Left quasi-normal band is contained in left semi-normal band. Left semi-normal band is contained in left semi-regular band. In a similar fashion, dual ones are like that. In between, rectangular band is contained in normal band. Normal band is contained in regular band. But if we are saying that one structure is contained in another structure, for example, see, we are saying that these are the two structures, and one structure is contained in another structure. And identity here is P1 is equal to Q1, and here identity is P2 is equal to Q2. For example. Then if you are saying that structure A is contained in structure B, it means that P1 is equal to Q1 implies P2 is equal to Q2. P1 is equal to Q1 implies P2 is equal to Q2. If P1 equal to Q1 implies P2 equal to Q2, we say that structure B contains structure A. Structure B is generalization of structure A. So if you are saying that, for example, if you are saying that left zero semigroup is contained in left normal band, then we have to prove that identity AX is equal to A implies AXY is equal to AYX. If you are saying that left normal band is contained in left regular band, it means that this identity implies AXY equal to AYX implies AX is equal to AXA. If you are saying that left regular band is contained in left quasi-normal band, it means that this identity implies this. If you are saying that left quasi-normal band is contained in left semi-normal band, it means that left AXY equal to AXAY implies AXY equal to AXY AY. in a similar way, axy equal to axy ay implies this identity. See, the line joining represents that this identity implies this. See, dots on the board, the type of bands. So this implies this implies this, this implies this implies this, like this. In a similar fashion, the dual ones are that. Dual means what? Means that, see, for example, if you say that ax is equal to a, the dual means what? A is commuting here from the left, and here a is commuting from the right. You say left normal band axy is equal to a by x, and yxa is equal to xya. In a similar fashion, you can see well that this is the dual of this. Is it clear? So you have to prove this. You have to prove. But in this, you can see that rectangular band is contained in normal band only when this identity implies this identity. That means you have to prove that x is equal to xyx implies axy a is equal to a by xa. And also you have to prove that axy a equal to a by xa implies axy a is equal to axa by a. Also, left semigroup implies rectangular band, means that ax is equal to a implies x is equal to xyx. Also, semi-lattice x equal to xy equal to yx implies left normal band. See, this is a connection. When the dots are joined by a line, an arrow is representing, it means what? This structure is contained in this. It means that if you have to prove this, you have to assume that semigroup S satisfies an identity, let S satisfy identity xy equal to yx. Then what is claimed? You have to prove that S will also satisfy this. Is it clear? So assuming this, you have to prove this. So you can start from the left hand side. It's very trivial. You can see that axy will be what? You have xy equal to yx. So you can change it. So it's trivial that xy equal to ayx. So semi-lattice is the left normal band. Also semi-lattice is a right normal band yxa. So xya, it is right normal band. But there is a no connection between semi-lattice and rectangular band. Means there is no connection between semi-lattice. Semi-lattice is not a rectangular band. Is it clear? It's not a rectangular. This identity does not imply rectangular band. Rectangular band does not imply semi-lattice. There is no connection. Well, you can see that. It is a left normal band. And left normal band and right rectangular band has no connection. You can see from the figure this. Isn't it? And also you can try by yourself. If you have semi-lattice, you can't prove the identity of rectangular band. If you have a rectangular band property, you can't prove a semi-lattice property. Is it clear? In a similar way, you can see that there is no connection between normal band and left regular band and right regular band. There is no connection. So you can't prove that this class is contained in this or this class is contained in this. But all classes are contained in bands. Of course, all are bands. So I have given all of you the exercise to verify this structure, verify this diagram, verify this graph. It means that all of you must try that you take this identity, let us satisfy this, and prove that this semigroup is left normal band. Left normal band is left regular band. Left regular band is left quasi-normal band. Left quasi-normal band is left semi-normal. Left semi-normal is left semi-regular. Dually, you can prove the right ones. Also prove between this. That is, the rectangular band is contained in normal band. Normal band is contained in regular band. In this way, you can, all of you can verify by yourself. Is it clear? So this is all about bands. One thing I also want to tell you more. Of course, it is not in your syllabus, but just for the sake of your understanding, what is going on, what is mathematics, isn't it? What is research? For sake of this, just I want to tell you something regarding this. For example, there is some concept of closeness that for example, that is left zero semigroup is closed. There is some definition of closeness. Now the question comes into the mind, this structure is bigger than this, and we have already proved that zero semigroup is closed. So can we prove this also as closed in itself? Yes, it is proved, it is closed in itself. Now again question comes into the mind, when some mathematics is proved for the smaller structure, can it be proved for the bigger structure, more general structure? That is called generalization. And yes, it is proved that left regular band is closed in itself, left quasi-normal band is closed in itself. Again, it is proved by semigroup theorists that left semi-normal band is closed in itself. It doesn't matter. So what is the definition of closeness? You need not to know this. What is closeness? Just I am telling you that what is going on. That this is mathematics. That is this structure is containing this, and this structure is containing this, and some mathematics is proved on the smaller structure. Now the question comes into the mind that can the same mathematics, can the same results can prove for the larger structures? So in this way, mathematics goes, and semigroup theorists have done, and also it contains this structure is very important. And whenever anyone of you goes in the research of semigroup theory, you will see that this diagram contains a lot of open problems still. So just for your knowledge, this I told you. This is not in the syllabus clauses and something like that, but just for the sake of your knowledge, I told you this, how the mathematics is going, what is mathematics. I already told you that first, that is we define something, then we give some examples, then it becomes meaningful, and then we do some results, then it is called mathematics. And if it has application, then it's okay. It may not have application, both things are that there. Now I am posing a problem, that is now I'm posing a problem here. Let S be a normal band. Then prove that AXYB equal to AYXB for every AXYB belongs to S. This is, I am posing a problem in front of all of you. That is AXYB is equal to AYXB. Means what you have to prove, what you have and what you have to prove. You have what you have, that is A square is equal to A, and AXY, A is equal to AYXA implies AXYB is equal to AYXB. These two conditions you have. And every element can be written as any square. A can be written as A square. AX can be written as AX into X. AX Y can be written as AXY into XY. It is like that because product of three element is again a single element of a semigroup S. Because it goes in S, it is a semigroup, isn't it? So you can consider also three elements as a one element, no problem, without loss. Anyway, so you have to prove that A square equal to A you have, and AXY A is equal to AYX you have. Now you have to prove that it implies that AXYB is equal to AYXB. Is it clear? So just I leave this problem to all of you. Try without loss, and discussion is welcome. Anyway, so I'm leaving you as an assignment. Now I will tell you some definition. subset T of a semigroup S is called subsemigroup if T square is contained in T. Is it clear? So a non-empty set T of a semigroup S is called subsemigroup of S. Subsemigroup of, you just write like this. This is called subsemigroup of S if T square is contained in T. That is, xy belongs to T for every xy belongs to T. Now next definition. All of you can think that what are the examples of such semigroups? It's very trivial. A non-empty subset A of S is called, left in bracket you can write right ideal of S if SA in bracket you can write just AS is a subset of A. Is it clear? And it is called two-sided ideal if SAS is a subset of A. Also, there is the fact that every ideal is a subsemigroup of S. Every ideal of a semigroup S is its subsemigroup. But conversely, but converse is not true. But converse is not true in general. Now more definitions. A subsemigroup S subsemigroup of semigroup S, which is a group, is called subgroup of S. Means a subsemigroup is a group with respect to the same operation on semigroup S. Then it is called subgroup of S. And what is the example? For example, you can say that S, as you can say, this is a full transformation semigroup, and this is what all functions from non-empty set X to X. This is a full transformation semigroup, and what is the subgroup? You can say like this. that is group of permutations on set X. G from, you can say any more set, say y to y, 1 1 on. This is group of permutations on set Y. Then, of course, binary operations are composition here. So, G is subgroup of S. So, this is group of permutations, and this is full transformation symbol. Full transformation symbol, correct? Map phi from S to T is called morphism or homomorphism. If X, Y, phi X, Y, phi